Okay, let's finish up the lesson from today that we did not get done during class. And I'm going to look at example 9 and example 10 with you. So it's finding positions and average velocity, things like that. So if a billiard ball is dropped from a height of 100 feet, its height s at time t is given by the position function. And then they're expecting us to be able to write this in. So we're going to play off of this standard basic position function. S of t equals -1/2. G is our gravity constant, t times squared. V sub naught is going to be the initial velocity, and S naught is the initial position. So this is the initial position. And if we read that again, we should be able to figure that out. And then this is the initial or the beginning velocity. So rereading this, a billiard ball is dropped from a height of 100 feet. That would be my initial position, wouldn't it? I'm 100 feet in the air. And it said it was dropped. So if you imagine that you have a hand and your hand drops this billiard ball and it's going down, it started with a velocity equal to 0 because it was just in your hand and it dropped down. So this would be 0 feet per second. That's always a tricky one to read. That velocity was 0 when it started. So S of t equals -1/2. The gravity force that I'm going to use, since I'm working in feet, is 32 feet per second squared times time squared plus our V naught was 0, so I'd have 0t plus my initial position of 100. Get familiar with that position function because we're going to be expected to write that quite often. If I boil this down just a little bit more, I would end up with -1/2 of 32. So here is -16 t squared plus 100 is my position function for this problem. Negative because it's going downward. We have a downward velocity or force from acceleration. All right, so part A. Number 1, part A. They want us to calculate average velocity. And you're just going to have to memorize what average velocity is. Average velocity is the change in distance over the change in time. Change of distance we also recognize to be like the change in the y value. And t is our independent variable just as x is. So kind of taking it back to the days of change of x or change of y over change of x. I'm on an interval from 1 to 2. So what I need to do is calculate out the ordered pair 1 comma something and the ordered pair 2 comma something. Remember, this is an interval notation telling me from time 1 to time 2. So when I put 1 into my position function, s of 1, I get -16 times 1 squared plus 100. That will calculate out to be an 84. So I get 84 as an ordered pair. My position function at time 2 will become -16 times 2 squared plus 100. And that would be 4 times 16, that's -64. 64, that'll produce a 36. So at time 2, it's at a height of 36. Now the average velocity is the slope calculation. Average velocity is equal to, you could do 36 minus 84 over the change in time, 2 minus 1. Definitely a negative average velocity, which is good because it's moving down. And I would get -48 feet per second. So that's on the interval from 1 to 2. Next, so that one turned out to be there. I'm just going to box it. That's our average velocity. Let's do the second one, part B, said from the interval 1 to 1.5. Well, for that, I need to know 1 comma something and 1.5 comma something. Go back to your position function. We already did this one earlier in part A, so that was an 84. Now, position function of 1.5 for a timestamp gives me negative 16 times 1.5 quantity squared plus 100. That, if you do your calculations, will turn out to be 64. So now I have the ordered pair 1.5 and 64. So calculating average velocity. Change of distance, 64 minus 84 over change of time, 1.5 minus 1. That gives me a negative 20 over 0.5. If I take 20 and divide it into halves, I'll get 40 pieces, so this will be a negative 40 feet per second. Okay, there's average velocity on that interval. Part C changes up the interval. Notice how these intervals keep getting a little bit tighter and tighter. Now we're just 1/10 of a second away from the initial time of 1. So I have the ordered pair 1 comma 84, but I don't know what 1.1 is when I put it in. So I put it into my position function and get out negative 16 times 1.1 quantity squared plus 100. And if you do that, you will get 80.64. 80.64. And if you do your slope calculation, I came up with an average velocity of negative 33.6. So velocity average was equal to negative 33.6. Number 2, the instantaneous velocity at time 1. Okay, instantaneous velocity. I need to see that position function. So part 2, instantaneous. Anytime I hear that it's at a precise instant, instantaneous velocity. This is really speaking about the first derivative. So I want to take the derivative of the position function. So I'm going to take my position function, s of t was equal to negative 16 t squared plus 100. I'm just looking up above to what we originally had written out. Now take the derivative, s prime of t, make sure you write that, is negative 32 power rule t, and then plus 0. So this is my velocity function, which is also the same as the first derivative of position function. At time 1, I believe is what they wanted, at time 1 second, I would have the velocity at time 1 is equal to negative 32 times 1, and that'll be negative 32 feet per second. If you wanted to see units on this, because I'm not being the clearest on that, gravity effect is feet per second squared. 1 second here. I get a second canceling that squaring, and that drops it down to feet over seconds. All right, interesting. Negative 32 feet per second, precisely at 1 second. As we watched this other intervals, as they closed in and got closer and closer to 1, notice only 1/10 of a difference. The average velocity was negative 33.6 compared to negative 30.0 at that precise spot of 1. Okay, example 10. I'll quickly run through this one. Using the derivative to find velocity. At time t equals 0, a diver jumps from a platform board that's 32 feet above the water. The position function of the diver is given by, and this, I believe, I thought I had it on here. So what we want to do is write this position function, except they did not give us all the information in the story. So I'm going to give you this position function. It was negative 16t squared plus 16t. There's the initial velocity that is not mentioned up in the story, but it has an initial height of 32 feet. So I'm able to conclude the 32 feet as the position, but the velocity initial was feet per second, 16 feet per second. When does the diver hit the water? Well, the diver hits the water when the height is 0. So if I'm at baseline here, my height is 0. This was 32. So I want to know when the position function is 0. Grab that position function we wrote up above, negative 16 t squared plus 16t plus 32. When does that equal 0? Well, the first thing I notice is they have 16 in common, so let's factor that out. Matter of fact, I'm going to take a negative with it. And it will GCF out that negative 16. And now we may factor this, and we get time minus 2 and time plus 1 equals 0. Two solutions coming off of this. I could have a choice of time equaling 2 and also at time equaling negative 1. Not so much for this particular problem, right? But we know that this general shape is parabola, and that's why we're picking up these two different time frames. The one we'll keep then is at time 2. When does the diver hit the water? At 2 seconds. What is the diver's velocity at impact? So part B, velocity at impact. Well, remember how long it took him to reach the water at position 0? S of t equaling 0 was time equals 2 seconds. Using that, we can calculate velocity. From the position function, I need to do the first derivative. That will take me into velocity. Get used to that. We're going to do it all year long. So S prime of t, looking up above here to this function, negative 32t plus 16, power rules for derivatives. Okay, there's our velocity function. We know it was at 2 seconds that he entered the water or reached the height of 0. So all we have to do is plug in the 2. How cool is that? So we get negative 64 plus 16. This sounds like it is a negative 48 feet per second. Negative because he was going downward. Fantastic.